Okay, so I mentioned that we wanted to talk a little bit about asymptotes. So given a formula for a function, I'm always going to want to check to see, does it have asymptotes? I'm pretty much almost always going to ask you to check for vertical and horizontal asymptotes. The only time I might not is if it's a polynomial. And if I do give you a polynomial, you can just say, it's a polynomial. Polynomials don't have asymptotes. But if I want to check for a horizontal asymptote, remember, when I have a horizontal asymptote, that's describing the end behavior of the function. So either as x goes off to infinity, we're approaching some number, or as x goes off to negative infinity, we're approaching some number. So if I want to check for horizontal asymptotes, I'm just going to evaluate both of those limits. The limit as x goes to infinity of f of x, and the limit as x goes to negative infinity of f of x. Okay. If either of these is a number, we have a horizontal asymptote at that height. If I don't get a number, I don't get a horizontal asymptote. Okay. Now, I do want you, if I ask you to check for horizontal asymptotes, I want you to show your work in checking on both sides. So let's just say, for example, that I was sketching f of x equals x times e to the x. Okay. Okay, so I've got to take these two limits. So I can say, let's take the limit as x goes to negative infinity of x e to the x. With this limit, I'm checking to see if there's a horizontal asymptote on the left side. Okay. So x is going to negative infinity, e to the x is going to 0. Okay. Remember, the graph of e to the x has its own horizontal asymptote on the left-hand side. Okay. So that gives me an indeterminate product. So I'd kind of like to get to an indeterminate quotient. I'm going to keep the x there, because if I have x, when I take the derivative, it's just going to become 1. If I divide by the reciprocal of x, it becomes 1 over x, and then the derivative gets more complicated. So I'm going to write this as the limit as x goes to negative infinity of x times over e to the negative x. By putting a negative exponent there, I say, oh, that's in the wrong place. That's actually an e to the x on the top. So now that's going to negative infinity. If x is going to negative infinity, the opposite of x is going to positive infinity, so that's going to infinity. Now I've got an indeterminate quotient, and I can use L'Hopital. So this is the limit as x goes to negative infinity of 1 over negative e to the negative x. Okay. E to the negative x, we said, was going off to infinity. So if the bottom's actually going then to negative infinity, but that means that the entire fraction is going to 0. Okay. So this limit is 0. So I know that the graph is going to have a horizontal asymptote on the left, just like e to the x does. Usually what I'll do, if I'm trying to put all the pieces together, is I would just make a note, that's a horizontal asymptote, so that I don't forget that once I'm ready to draw the final graph, because usually we're going to be checking for all sorts of things. Of course, if I had a horizontal asymptote at a different height other than 0, I would just draw it in as a dotted line. Okay. All right. Now, it feels like we've done a lot of work because we used L'Hopital's rule, which we will be using a lot in this section, and we're largely going to be using it in this step of checking for horizontal asymptotes. Okay. We're not done, though, because we only checked on the left-hand side. I need to check both sides. So I would say, what's the limit as x goes to infinity of x times e to the x? Well, x is going to infinity. E to the x is going to infinity. Big times big is big. Positive times positive is positive. This is going off to infinity. So there's no asymptote on the right-hand side. But I do want to see that work for you checking it. Okay, so that's our horizontal asymptotes. Also want to talk about vertical asymptotes. And there are two ways that we could end up with a vertical asymptote. The most common one is if A makes the denominator 0, but not the numerator, then the vertical line x equals A is a vertical asymptote. I'm just going to write VA to abbreviate vertical asymptote. Okay. So, as an example, if I had f of x equals x squared over x minus 2, I can see 2 is going to make the denominator 0. It doesn't make the top 0. So I would have a vertical asymptote at x equals 2. Okay. I do need to check whether it makes the top 0, because if you remember a while ago we had e to the x times x over x. So 0 made the bottom 0, but it also made the top 0. So I was able to cancel and just get e to the x with x not equal to 0. So that corresponded to a whole rather than an asymptote. But basically, if you've got a value that makes the denominator of a fraction 0, it's not in the domain. It's either the location of a whole if you can cancel it out, or it's the location of an asymptote if you can't. Okay. All right, the other way we could have an asymptote is if one of what I'm going to call our building blocks has a vertical asymptote. Now, what do I mean by that? Well, let's suppose I had f of x equals the natural log of x plus x. Now, I'm thinking of this as a function that I've built out of these two building blocks, the natural log of x and x. I combined those pieces using some arithmetic, so that was my building tool, okay, to build this function. Now, x is just a polynomial. It's actually a line. It doesn't have any asymptotes. But I know that this one has an asymptote. It has an asymptote when x is equal to 0. And sometimes when a function has its asymptote, it grows very attached to that asymptote. And when it goes on a play date with another function, it wants to bring that asymptote with it. So we have to check. So, because this has an asymptote at 0, that means I know that as I approach 0, and it would have to be from the right, otherwise it wouldn't be in the domain, this piece is going to negative infinity. So I would just have to take the limit as x goes to 0 from the right of the entire thing to see whether this piece going to negative infinity drags the whole thing down with it or not. So let's see. This piece would be going to negative infinity. This piece would be going to 0. Now, I can't literally do that arithmetic because arithmetic is a property of numbers and infinity is not a number. But I can use some common sense and say, hey, if I've got something big and negative and I add something really small to it, I've still got something big and negative. So this function would have a vertical asymptote when x is equal to 0. However, if you remember earlier on, I think it was in the last video, we looked at f of x equals x times the natural log of x. In that one, we used L'Hopital to evaluate the limit, and we got that that limit was equal to 0. So this one had no vertical asymptote. So here, even though that same building block function had a vertical asymptote, it didn't bring it with it. Okay. So it may or it may not, and you simply have to check. So anytime you're looking at your function, you just want to look at what pieces did you build it out of. If any of those has a vertical asymptote, you need to check the location of those asymptotes and take the limit as you approach those values. Okay. Most often, the asymptotes that we're going to encounter are going to be from case 1, where we've got a number that makes the denominator 0, but not the top. The last type of asymptote we're going to take a look at is slant asymptotes. So that's when we have a diagonal line that serves as an asymptote. There are lots of types of functions that can have that. The most common, though, is just a rational function, And I'm going to hold off and wait to cover that until we get to an example that actually has one. Okay, but we will be covering that. That's just coming later. I'm generally not going to ask you to check for these for most functions. I do expect you to know how to find them, but you can expect if I'm asking you to find a slant asymptote or check for it, probably it's a situation where there actually is one. Okay, next video we're going to try to put all these pieces together and graph a function.